Hello, so now we're going to talk about reaction stoichiometry. So stoichiometry kind of sounds like a big scary word, but all it is the relationships between the amounts of reactants and products in a chemical equation. So it's really just something also called a stoichiometric factor, and that is the ratio of those coefficients in a chemical equation that's used to relating the amounts of reactants and products in that chemical equation. So when we're talking about stoichiometry, all we're really talking about is using the relationships between the amounts of starting material and products in a chemical equation in order to do calculations, like calculating theoretical yield, limiting reagent, and things like that. So to kind of put it in perspective, the book has something that's a non-chemistry example. So that example is just a recipe for pancakes. So to make 8 pancakes, you need 1 cup of the pancake mix, 3/4 cups of milk, and 1 egg. So and that will all combine to make 8 pancakes. But if you have a bigger family or you're just really hungry, you might want to make more. So if you want to make 16 pancakes, how many eggs would you need? And so, as you can see, there's a relationship between the number of eggs and the number of pancakes. And that is that for every 1 egg, you can make 8 pancakes. So if you want to make 16 pancakes, you would then multiply that by that relationship. So 16 pancakes times 1 egg per 8 pancakes. So 16 divided by 8 times 1, and you get to 2 eggs. So if you wanted to make 16 pancakes, you'd have to double the recipe, double the amount of eggs, and you would need 2 eggs. Likewise, if you wanted to figure out how much milk you would need, you would just use the relationship between milk and pancakes. So it's for every 3/4 cups of milk, you can make 8 pancakes. So 16 pancakes times 0.75 divided by 8, you would need 1.5 cups of milk in order to double that recipe. So in order to then move over to stoichiometry in chemistry, there are 2 things that you need. 1, you need a chemical equation, but most importantly, you need to make sure that you have a balanced chemical equation, because stoichiometry are all about those ratios of reactants to products. So if you don't have a balanced equation, then you're not going to have the right relationship. So make sure you have a balanced equation. And then you're just going to use those stoichiometric factors or ratios in order to calculate the desired quantity. So I drew up this picture. It's also in the book. In a chemical equation of reactant A going to product B, there are a bunch of different things you can calculate. So if you're starting with moles of A, you can get to moles of B directly using that stoichiometric factor. And then from there, you can do a whole bunch of branching off. So from moles to B, that should say mass of B, not A, sorry. From moles of B, you can get to mass of B. You can then get to the volume of B using the density. From moles of B, you can get to the volume of B in a solution using the molarity. You could also get to the number of particles of B using Avogadro's number, and you can do the exact same thing for all of A's value. So mass of A to volume of A, moles of A to volume of A in solution, or from A to the number of particles of A. So again, this is in their book, but it's pretty nifty. But let's do some examples, because that's the easiest way to get the hang of this. So starting with an equation of aluminum plus iodide going to aluminum iodide. So looking at that equation, we can see that it's not balanced. So there's 3I here, only 2I here, so we need to balance it. So I'll just put a 3 there, put a 2 in front of there. Now there's 6 iodine on each side, and now we would just need to put another 2 in front of aluminum, and now we have a balanced equation. So looking at this equation, if I were to tell you that you want to start with 0.429 moles of aluminum, how many moles of iodine would you need to run this reaction? So we're wanting to start with moles of aluminum, and we want to go to moles of iodine. So then that's when we use those stoichiometric ratios. So we're starting with 0.429 moles of iodine all over 1, and then you're going to multiply it by that ratio. So for every 3 moles of iodine, there are 2 moles of aluminum. And if you do this math of 0.429 times 2 divided by 3, oh, whoops. Thought something looked off. We're starting with moles of aluminum, not moles of iodine. So, moles of aluminum times, so then that would also flip that ratio. So now there are 3 moles of iodine for every 2 moles of aluminum. So it'd be 0.429 times 3 divided by 2, and that will give you 0.644 moles of I2. So if you want to completely react 0.429 moles of aluminum, you would need 0.644 moles of iodine. Okay, so that's kind of the most basic example, but we can make it more complicated. Let's look at this example of C3H8, or propane, plus molecular oxygen going to carbon dioxide and water. So first things first, we need to balance this equation. So we have 3 carbons on this side, so put a 3 there, and we have 8 hydrogens, so put a 4 there. And so now we have 10 oxygens, so 6 on here, and then 4 there. So if we just pop a 5 right there, we have a balanced equation. So now, what if I were to tell you you're starting with 0.75 moles of propane, and I want to ask you how many molecules of carbon dioxide will form? Okay, so we're going from moles of propane and we're going to then need to go to moles of carbon dioxide, and then from there we can go to molecules of carbon dioxide. So starting with 0.75 moles of propane, we would then multiply it by the stoichiometric factor that relates propane to carbon dioxide. So for every 1 mole of propane, we will form 3 moles of carbon dioxide. And then to get to molecules, for every 1 mole of carbon dioxide, that's when Avogadro's number will come in. There will be 6.022 times 10 to the 23rd molecules. And if you do that math, so 0.75 times 3 times 6.022 times 10 to the 23rd, you will find that you will form 1.4 times 10 to the 24th carbon dioxide molecules. Okay, so that is the slightly more complicated example, but it can get even more complicated. So we'll do one more examples with just plain stoichiometry. So let's do C8H18, so octane, plus oxygen going to carbon dioxide plus water. Once more, gotta balance this guy. So 2 carbons, 2. Now we have 36 carbons. So we would put 36 hydrogen, sorry, plus 18, and that would get you to the 36. And then to have the right number of oxygen, which is 50 in this case, we would then put a 25 right there. So now, if I say that 702 grams of octane is going to react, and I want to know the mass of oxygen that is consumed in that reaction. So we're going from mass of octane. Now we want to figure out something that has to do with oxygen, and so we'll need to use that stoichiometric ratio, and that involves moles. So we'll then need to convert to moles of octane. Then from there we can get to moles of oxygen, and then from there we can get to the mass of oxygen. So first steps first, we're starting with 702 grams of octane. So to get to the moles, we'll use the molar weight, which I've already determined. So 1 mole of octane is equal to 114.23 grams. So that's the mole of octane, and now we need to relate octane to oxygen. So for every 2 moles of C8H18 or octane, we would also need, not generate, we would need 25 moles of oxygen. Oops, sorry, that keeps slipping. Now, we would then use the molecular weight of molecular oxygen to get to the grams there. So then 1 mole of O2 is equal to 32.00 grams. And when we do that math, we would figure out that in the course of that reaction, we would consume 2.46 times 10 to the 3rd grams of oxygen. So that's one of the more complicated examples. And then you'll get much more hands-on experience with this in your homework. So that is just plain stoichiometry. But another way that we can apply stoichiometry is in determining reaction yields. So you'll use stoichiometry to determine, and there are a couple of different key terms. And one of that is the limiting reactant. So the limiting reactant is the reactant or reagent that is present in an amount lower than is required for a perfect stoichiometric ratio. So since there's less of it, it's going to limit the amount of the reaction that can take place. The reaction will go until the limiting reactant completely runs out, and then it will stop. On the other hand, the excess reactant is the reactant that is present in more than the amount that's needed. So the reaction will go until the limiting reactant is completely run out, and then there will be still some of that excess reactant left over. So the easiest way to kind of describe this is to just do an example. So an example that I have, here it is 3 silicon plus 2 nitrogen gas will go to Si3 and 4 solid. So if we put in a reaction vessel, let's say 2 grams of silicon and 1.5 grams of nitrogen, which one of these would be the limiting reactant? So the way we would determine this is to figure out how much product each of these could theoretically make. So if we're starting with 2 grams of silicon, so 2 grams silicon times the molecular weight of silicon, which is 28.09 grams per 1 mole. That will get us to moles of silicon times their ratio. So for every 3 moles of silicon, we generate 1 mole of product. We would then create 0.0237 moles of product. So if all of the 2 grams of silicon reacts, we would generate 0.237 moles. On the other hand, if we have 1.5 grams of nitrogen over 1 times the molecular weight of nitrogen, so 28.02 grams per 1 mole, times the stoichiometric ratio between those. So for every 2 moles of N2, we generate 1 mole of product. In this case, we would make 0.0268 moles of product. So if all of the 2 grams of silicon react, we make 0.0237 moles of product, and if all of the 1.5 grams of nitrogen react, we'll make 0.0268 moles of product. So silicon is able to make less product than the nitrogen, so silicon would be the limiting reagent. And then on the other hand, nitrogen would then be the excess reagent. So all that really means is just that the silicon will completely react, but will run out of it. And then even though there will still be some nitrogen left over, there's no more silicon present for it to react with. So it'll just stick around and be left over. Okay, so that's limiting and excess reagent. The last thing we're going to deal with is something called percent yield. So percent yield, we've done it in the lab a bunch. It's just the amount of product you've actually made divided by the theoretical yield. And so the theoretical yield is the amount of product that you can make in theory. It's what you'll calculate using those stoichiometric ratios. So the theoretical yield of this reaction would be that 0.0237 moles. In theory, we could make exactly 0.0237 moles, but in reality, when you go into the lab and you run a reaction, things go wrong. Reactions don't always go all the way to completion. And so that's where we get the actual yield. It's the amount that we actually make. And so in order to calculate that, you'll take your actual yield, what you actually get in lab, divided by the theoretical yield, what you could get in theory, times 100. So we're going to do just one more example for that. There's my little eraser. Okay, so the example that I have is if you have copper sulfate, which is aqueous, plus solid zinc, you will generate some solid copper and then zinc sulfate. Okay, so if we are reacting 1.274 grams of copper sulfate with excess zinc, we already tell you that the zinc is in excess, so you don't have to worry about which one's the limiting reagent. So it's 1.274 grams of copper sulfate in the presence of excess zinc. You run this reaction and you collect 0.392 grams of copper. So that's the amount of product that you actually get. What is the percent yield? So in order to figure this out, we need to calculate the theoretical yield. So we're starting with 1.274 grams of copper sulfate. You would then need to multiply that by the molecular weight of copper sulfate, which I have here as 150 59.62 grams per 1 mole of copper sulfate. Then relate that to the amount of moles of copper, and it's a 1-to-1 ratio. For every 1 mole of copper sulfate, you generate 1 mole of solid copper, and then get to mass of copper. So for every 1 mole of copper, it is 63.55 grams of copper. And you do that math, you will get that the theoretical yield is 0.5072 grams of copper. So then the percent yield would be what you collected, so the actual yield. So 0.392 grams divided by the theoretical yield, 0.5072 grams times 100, which in this case is 77%. So then that would be the percent yield. So that is stoichiometry. Put any questions that you might have in the comments, and I will answer them as fast as I can.